Let's start again with a voltmeter across a battery. So now what you have here is a real battery. So the real battery should have a EMF. Here it's 6 volt plus an internal R, that's 1 ohm. So you've got a 6 volt 1 ohm battery. The endpoints of these of this entire cell are A and B. So A and B are the terminals that are visible to you outside, right? And everything else is inside. The EMF part as well as the internal R, everything is inside the battery. A and B are visible outside, and you can think of it like a car battery maybe, where you see two protruding electrodes outside. So those electrodes are A and B, and you just want to measure the EMF of that battery with the help of a voltmeter, and so you use a voltmeter in the circuit. And the voltmeter that you have decided to use is having a huge R. R is probably 999 ohms and internal R is only 1 ohm, so I can say that the resistance of the voltmeter is much larger than the internal resistance of the battery. And let us try to figure out what the reading of the voltmeter will be. So it's simple here. You will see that the current will be 6 by 1000 amps, because this 999 ohm and 1 ohm will be in series, so their equivalent will be 1000 ohms. So I is equal to 6 by 1000, that's 6 milliamps. And the voltage drop across AB can be calculated either from the voltmeter branch, and if you want to do that, you just have to do a I times R, so 6 milliamps into 999. Or if you use the cell branch, you can do E minus IR. So E minus I and internal resistance R, and both will give you the same number. This number is called the terminal voltage across the cell. And this is exactly what even the voltmeter is going to read. So the voltmeter, you will see, is not going to read 6 volts, people. It's only going to read 5.994. And that is a big problem, because you were interested in measuring the EMF, but what you have ended up measuring is the terminal voltage. And this result will be true irrespective of what kind of a voltmeter you put in here, because any real voltmeter will have a non-infinite value of resistance, and when that happens, there will be a current flowing in, and because there is a current flowing in across A and B, you will never have EMF. You will always have only the value of V, which is E minus IR. So keep in mind that EMF of a real cell can never be measured directly using a voltmeter. You can't do it. Right, so indirectly we can figure out what is the EMF, and I'm going to show you that experiment. So please keep in mind this word directly. So we will not be able to directly measure EMF using a voltmeter. We can indirectly find it out using a voltmeter. We can also indirectly find it out using some other measurements with the help of other instruments. We will go to them immediately after doing the voltmeter stuff. But just to show you how we can find out the EMF indirectly using a voltmeter, I have shown you this circuit. So what happens in this circuit here is, you've got a cell, and the cell is represented by a blue boundary, and you will see that some part of that blue boundary is overshadowed by the brown strokes here, right, which show the voltmeter joined to the battery, the ends of the battery really. So here you have a battery with EMF E, and internal R is also given, that's small r, and there is an emitter put in the circuit, and there is a rheostat, and the rheostat has got a sliding contact. As the sliding contact moves to the left or to the right, the rheostat resistance that is present in the circuit changes, and if that changes, the current in the circuit will change, so the emitter reading changes. But if the current in the circuit changes, then the current flowing through internal R also changes, and when that happens, the voltage drop across these two endpoints X and Y, that also changes, because the voltage drop across XY will be E minus IR, right? So I will also change when I change the value of the resistance introduced in the rheostat. Now, so keep in mind that I'm going to measure I using the ammeter, and I'm going to measure delta VXY using this voltmeter. So the voltmeter is going to give you the voltage difference between X and Y, and we will plot them. Before plotting them, we will just try to figure out what kind of a plot do we need. So we will put this term on the left hand side itself, and on the right hand side we will rearrange. We will write it as minus R times I plus E, which you now see follows Y is equal to mx plus C, where the role of Y is played by V, M is played by minus R, I is played by X, and E is played by C. So if you try to plot the points that you get, so what you do is you do this experiment over again and again, once with the sliding point somewhere, then you shift the sliding point on the rheostat somewhere and you get a different value of I and delta V. Then you shift the sliding point somewhere else on the rheostat, you get a different value of I and delta V. So you will keep on getting different values of I and delta V. You plot them and you will get a scatter diagram like this. It will be a scatter plot. So you will get all these many points. And with all these many points, you will have to draw a line of best fit. So once you draw the line of best fit, you will see that this line will intersect the y-axis at a certain place. That's the y-intercept, and so that is the EMF of the cell. But that point will never be obtained in the data, right? And if you figure out the slope of this line, you will see that the slope is negative. So that negative value will be equal to minus r, which means if you throw away the minus sign, if you only take the magnitude of slope, that will give you the value of r. So you can find out the EMF and the internal resistance of a real cell using an ammeter voltmeter combination and taking multiple readings and plotting a graph between V and I. Let's go over to the next part, people. So what we do is, in order to figure out the EMF of a cell without taking multiple readings like what we had to do in case of the voltmeter ammeter apparatus that we were using, we use an instrument called the potentiometer, and it is just a wire. So this orange colored wire which I am showing you here is the specific equipment that we are talking about, and it's called the potentiometer wire. There is a cell E0 that drives this entire apparatus, and this cell E0 is often called the driver cell. There is a key somewhere. The key has not been inserted in this picture, but when we insert it, we will show a dot inside here, right? So that will show you that the key has been inserted and the circuit is closed. When the key is not there, the circuit is open. The wire here has got a length L0. Now what happens if I close this key? Now the usual expectation is that if I close this key, the circuit is closed and there is a EMF, and because all of these are wires, so there is going to be zero amount of resistance in the circuit. So the current will be infinity, and infinite current is, it leads to infinite heating, and so the circuit will burn, or the wires will melt as soon as the key is closed. But that's not what is going to happen here, because this wire AB is no ordinary wire, right? So this wire AB, we have designed it to have a significant value of resistance. Now R is equal to rho L by A, and we need to have this number very large. So what we do is we take a wire of very large rho, very long length, and very small area. Now very small area would mean that it should be a thin wire. So you will often see that this is a very thin wire in the lab. And length is high, which means this L0 is usually 5 to 8 meters, right? And 5 to 8 meters is not easy to contain in a straight line. So what we do is we break that 5 to 8 meters long wire in segments of 1 meter length each. So here I'm showing you what happens for an 8 meter long wire. We have broken it up into 8 segments of 1 meter each. So you've got 8 orange wires, 1, 2, 3, 4, 5, 6, 7 and 8. And these 8 orange wires are joined to each other as shown. The uppermost wire is joined to the higher voltage end of the battery here, and the current flows in this uppermost orange wire. And then there is a very thick metal strip of very small length, right? So why are we using a very small strip, and it should be thick also? Because we want the area to be large. If it is thick, the area is large. It's short, so the length is small, and because it is a metal strip, rho is actually very less, and rho L by A is very small, so the resistance of this strip tends to 0. So this thick strip here and all the other thick brown strips here do not affect the reading of your instrument, right? They contribute to 0 resistance. That's the whole idea. And the other end of this orange wire here is joined to the negative end of the cell with the help of a key, and this cell here is called the driver cell, right? So it's usually called the driver cell. Now a word about rho. You know that the values of rho usually for metals are of the order of around 10 to the power minus 8, but this orange wire that we have chosen here is some specific kind of alloy, and it is mostly nichrome. It's nichrome wire. Nichrome wires have usually rho of around 10 to the power minus 6. That's 100 times the resistivity of the usual metals like copper, silver and aluminum and so on. So the resistance of 8 meter of this wire is expected to be at least 100 times that of 8 meters of copper wire, right? And that is a significant difference, people. So we cannot ignore the resistance of this orange wire. We will keep that into account, and then we will solve for anything else. So this is how the apparatus looks like in a lab, right? But then we will usually show it in all the pictures and all the diagrams like this for simplicity. And you can keep in mind that the length AB will be approximately 5 to 8 meters, something of that kind, right? And we usually deal with that length in terms of centimeters, so 500 to 800 centimeters or something. And how this apparatus works is shown to you using a very simple example, right? So I have chosen AB to be 600 centimeter long, and I have taken the driver cell to have 6 volts EMF, and the key here is closed, and I'm just assuming, so this is the voltage assigning method, people. I'm just assuming that the top right corner is at 0 volts. And because the pink thing is just a wire here, it is only a connecting wire, so B also should be at 0 volts. And all this wire up to the lower end of the battery is at 0 volts, then 6 volts on the other side, and this whole wire is at 6 volts, 6 volts up to A, and so A is also at 6 volts, but then the voltage drops from 6 volts at A to 0 volts at B as you move across this orange wire. That's a very thin wire, so to say, And let me just try to show it to you using expressions. So resistance of AB wire is rho L by A. So therefore the voltage drop in AB wire is I times rho L by IR. We know that equation. And you will see that the voltage drop divided by length. So from the right hand side I am taking length to the left hand side. I will get I rho by A. And I can strive to make this term a constant. Right, now how can I make this term a constant? I can make this term a constant, I rho by A constant, if the wire is homogeneous. If the wire is perfectly homogeneous, the same material throughout, then rho is going to be a constant, no doubts about it. Right, so anywhere you look into the wire, the rho will be the same, wherever you have a look. Fine. Then if you have used a wire of constant area of cross section throughout, then A is also a constant. And it is for this specific thing that we don't really bend the wire. I would have shown you the apparatus on the top here somewhere, right? So what I could have done is, instead of having this thick metallic strip, I could have turned the orange wire, right? And I'm showing it to you here somewhere. So I could have had the orange wire turning, but then when the orange wire takes a turn, it becomes flatter at the turn like this. You would have noticed this when you bend a wire. At the place where it bends, it becomes a lot flatter and it becomes thinner. So the area of cross section definitely can change, and we don't want this effect to be there. Now the area of cross section can change because the volume is not really a constant, because there are imperfections inside and volume does change. We have learned that in an earlier chapter on elasticity. So let's not argue that the area might be the same. The area may be the same, and the area may not be the same. We are not sure, but a good way to be sure about is not to bend the orange wire and join it using thick strips. Right, so we indeed join it using thick strips. And the last thing is, the wire should not be allowed to heat up, because you know that if you heat up a piece of electrical wire, then the increase in the temperature messes up with the electrical properties of the wire. So rho changes because tau changes, right? And also the amplitude of oscillations of the lattice ions will change, and so on. So we don't want the wire to heat up. If the wire is not allowed to heat up, then rho is a constant and I is a constant. And you have to understand the difference between 1 and 3. Now 1 says that the wire is homogeneous, so as you move along the wire, rho will be a constant. So the rho at a certain place near A and rho at a certain place near B will be equal, or anywhere else on the wire will also be equal. When I talk about the heating, it means rho of that entire wire now and rho of that entire wire after some time, after getting heated up, they should be equal, right? And how can I avoid the heating up of the wire? I can avoid the heating up of this wire by keeping the key closed only for a short duration, during which I have to take the reading. Once the reading has been taken, I need to unplug the key, right? And then delta VAB by L will be a constant, and I use that property in this experiment. So delta VAB by L is a constant. Now this, if you look at this term, shows you the rate at which the potential decreases from A to B with respect to length of the wire. So this is rate of change of voltage per meter or for a unit length, and this term has been named the potential gradient along the wire. So keep this in mind, it's called the potential gradient along the wire, and this property is the working principle of the potentiometer. So if they ask you, you should be able to write this: the potential gradient across the potentiometer wire is a constant. Fine, not a huge deal. Now let's go back to our example, people. The example was the driver cell of EMF 6 volts, and you have a wire AB of length 600 centimeter. The left hand side is at 6 volts here. The right hand side has been grounded, and so VB is 0, VA is 6 volt, and if the potential drops at a constant rate throughout this wire, then I can figure out what the potentials at all these points D, E, C, F, G, B, all B, because I know that if I have all these points equidistant from each other at a distance of 1 meter each, so from A to D is 1 meter, and the drop in voltage is also 1 volt. So D should be at 5 volts, E should be at 4 volts, C should be at 3 volts, F should be at 2 volts, G should be at 1 volt, and B should be at 0 volts. That fact can be ascertained using this. You've got a 6 volt drop from A to B, so across a length of 600 centimeters. So you have 6 volts dropping in 6 meter, or 1 volt per meter, or 1 volt per 100 centimeter, or 0.01 volt per centimeter. Right, so that's the term that we should be interested in. We should always be interested in this term, which is called the potential gradient. Right, and then let me show you the working of this instrument with the help of, again, the same example, but some additions are made to it. Now this apparatus, you will see the orange and the pink one is the same apparatus which I have explained to you here, right here in this place. But then I have made a few additions, and what I have added are this brown wire attached to this cell is equal to 2 volts, and there is a galvanometer, and there is a thing called jockey. A jockey is a sliding contact point. It can create a sliding contact point having 0 resistance, people, because a jockey is very thick really, and it has got a broad end which can be slid over this wire without losing contact with the wire. Right, so what I'm going to do now is understand first the fact that if A is at 6 volt, then the left hand side wire here is at 6 volts, and then across the cell you have got a drop of 2 volts. So on the right hand side of the cell I have got 4 volts, and now I have galvanometer, and there is a jockey, and if the jockey is in air, then it's a broken circuit and no charges can flow in this branch. Right, nothing will happen to this branch, so no current in this branch. But the moment I keep the jockey in contact with this orange wire, current will start flowing in this entire brown segment. And how will it flow? Suppose I keep the jockey in contact with the 5 volt point. Then you see that there is 5 volts on the right hand side of galvanometer and 4 volt on the left hand side of galvanometer. So there will be a flow of current from the right hand side, that's higher voltage, to the left hand side to the lower voltage, and maybe the galvanometer will show me a leftward deflection because the current flows like this. Let's just assume that it is going to show us that kind of a deflection. And maybe if I put the jockey in contact with some other point, the same circuit, I have put the jockey in contact with the 2 volt point here, then on the right hand side of galvanometer I've got 2 volt, on the left hand side I've got 4 volt, so the current should flow from the higher voltage to the lower voltage point. Of course it's not that simple, but then you will be able to see that there will be a current from the left hand side to the right hand side, and the needle will show you a rightward deflection. So how we go ahead with the experiment is, we keep the jockey in contact with the wire at various places, and we figure out at what places is the needle going leftwards, at what places is the needle going rightwards, and there will be a point in between somewhere where the needle will not show you any deflection. So any guesses, people, where in this circuit should I keep the jockey in contact so that the needle of galvanometer does not show me any deflection? At which point? So as all of you have understood, I should put the jockey in contact with E. And if I put the jockey in contact with E, then what happens is the right hand side is at 4 volts, the left hand side is at 4 volts, and there is no current flowing in the galvanometer because it's the same voltage at the two ends of the galvanometer. And if there is no current in the galvanometer, it makes sense to say that there will be no current through the cell also here, right? The 2 volt cell. And by the way, the 2 volt cell is called the auxiliary cell, right? So here the one which was attached to this orange wire up was called the driver cell, and this one, the brown one, is called the auxiliary cell. And you know that for this auxiliary cell, I should actually have an equation of this kind: V is equal to E minus IR, but I is 0, so V will be equal to E. So if you put the jockey in contact with an appropriate point on the wire AB, and that appropriate point here was E, then there will be no current flowing through this cell, and the drop across this cell will be equal to its EMF, and that will also be equal to the drop between A and that appropriate point E. And that appropriate point on the wire AB is called the null point. So hereafter we will refer to that point as the null point, where if you put the jockey in contact, there is no deflection in the galvanometer. Right, so that's one. Now how do we use this fact with variables? So let me explain to you this experiment, people. The first thing that we will use the potentiometer for is finding the EMF of an unknown cell. Right, so let's say this is experiment A, and I'm saying experiment A because I will be referring to this experiment again and again in future. So let's call this experiment A, and there is a driver cell of EMF E0 which has been joined to this wire AB with the help of a key. When the key is closed, the driver cell E0 will drive a current in this wire AB, and there will be a voltage drop across AB, and I can figure out what is the voltage drop per unit length. So E0 volts will drop in AB, and the length of wire AB is L0. So E0 divided by L0 is the potential gradient, right? E0 divided by L0 will be the potential gradient. Now I've put another cell, the auxiliary cell, whose EMF is E, which is unknown right now, and I want to measure it. And this cell has been kept so that the higher voltage ends of the two cells are connected together at the same point. So keep in mind that whenever we are dealing with the working of a potentiometer, the ends of the cells that must be joined together at the same point should be of the same kind. So either the higher voltage end and the higher voltage end should be connected to it, or you can invert it. You can invert the upper driver cell, but then if you invert the upper driver cell, you also have to invert the auxiliary cell, so that the lower voltage ends of both these cells will be then connected to it, right? And both the apparatuses will make sense. But anyhow, we will join this cell, auxiliary cell, like this. There is a galvanometer and there is a jockey, and I'm just assuming that I have put the jockey exactly in contact with the null point C, right, with the help of trial and error method. So after doing a lot of trial and error, I have put the jockey in contact with C, and the distance from A to C is L. Now I know that the drop that happens across this auxiliary cell is equal to its EMF, right? So the drop is equal to its EMF, and that same drop will happen across AC. So I know that EMF is now the drop across AC, right? And then I can say E0 by L0, which is the potential drop per unit length. So and I have to find out the potential drop for a unit length. I'm using the total EMF by the total length, and my desired drop by the desired length which I have got using my experiment. So this is E by L, and so E0 by L0 is equal to E by L. This is the expression which you will get. So knowing the value of E0, L0 and L, you can figure out the value of E, right? So this is one, and let me finish off one small segment and then I will give you time to write notes, people. Let us then see how this apparatus can be used to compare EMF of two cells. So how can I compare EMF of two cells? There are two methods. One is of course the brute force method. So keep in mind that the experiment that I have just now described, I have labeled it as experiment A. So suppose I do this experiment A with a cell of EMF E1 and I find out what E1 is. And if I do this experiment A again with a cell of EMF E2 and I find out what EMF E2 is, then my job is done. Right. So the idea is to perform experiment A with cell E1 and get its balancing length L1, and then with the cell E2 and get the balancing length L2. Right. So you would have now understood the use of this word, balancing length. This is the length from point A, which is one end of the potentiometer wire, to the null point. This entire length is called balancing length, people. So what I will do is I will find out the balancing length for the two cells E1 and E2, and I know that E0 by L0 will be equal to E1 by L1, and E0 by L0 will also be equal to E2 by L2. So in effect, E1 by L1 will be equal to E2 by L2, and I will get E1 by E2 is equal to L1 by L2. This is the brute force method. You are not doing a lot. You are just repeating experiment A with two cells individually, and you are getting the answer. But sometimes, just to check your physics acumen, what they do is they use a more interesting method, and I'm not saying that it's a better method, I'm just saying it's a more interesting method because it indeed is more interesting. So what they do is they take two cells E1 and E2 whose EMFs have to be compared, and they use them in the circuit at the same time, and I'm showing this to you using values here. So what they do is, suppose you have got a driver cell of 15 volts, and you have assumed that the right upper end here is at 0 volts. So then you have got 15 volts here, 15 volts here, 15 volts here, no issues. And let us take some example values. E1 is maybe 5 volts and E2 is maybe 2 volts. So starting from 15 volts, if you go across E1, you will get a drop of 5. So you will get a voltage here which is equal to 10 volts. Then from 10, you have a drop of 2 volts, so you get to 8 volts. And I will have to now keep the jockey somewhere on this wire AC where the voltage must be 8 volts. So at C, if the voltage is 8 volts, then I'm not going to get any current through the galvanometer, and these two cells will be balanced against a length AC of the potentiometer wire. So they will take this reading once. So now what you have done is you have joined the two cells E1 and E2 in the same manner exactly, and you have found out the balancing length L1. And this length L1 is going to balance E1 plus E2 volts. So E1 plus E2 is being balanced at L1, and that is equal to E0 by L0. And in the next apparatus, what they do is in the next experiment, what they do is they just invert E2. They invert the smaller EMF. Right, so they invert the smaller EMF, and then what happens is, so you should have an idea of who the smaller EMF is out of E1 and E2. So once you invert it, you will see that starting from 15 on the left hand side, you go to 10, and then you have an increase of 2. So now you have to find a point on this wire AB where the voltage happens to be equal to the 12 volts here. So that's the point where you should find the null point. Now the length up to that point is L2, let us say. Now I know what is the net EMF which is being balanced against this length L2 of the potentiometer wire. That's E1 minus E2. So E1 minus E2 is being balanced against a length L2, and that is equal to E0 by L0. So I get E1 plus E2 by L1 is equal to E1 minus E2 by L2, and I bring E1 minus E2 to the left hand side, L1 to the right hand side, use componendo and dividendo, and you will get E1 by E2 is equal to L1 plus L2 by L1 minus L2. So that's how you can try to compare the EMFs of two cells using the potentiometer. Now we have found out the EMF of one cell, we have compared the EMFs of two cells, but we haven't found out the internal resistance of a cell, and that is exactly what we are going to do now. So finding internal resistance of a cell using, of course, the potentiometer. So how does this method work? You have again got the same kind of circuit. So you have got a driver cell E0, then you have got a key, and you have got this special wire that we are talking about. So that wire is AB, put somewhere here like this, right? And A is on the left hand side, B is on the right hand side, and the wire closes like this. Then you have got another auxiliary cell, that's E. Let me take the auxiliary cell here. So that's E here, and now this guy E has got a R, and in this circuit you have put a galvanometer somewhere, and attached to the galvanometer is a jockey that goes to some point. And what you have done now is you have attached another blue segment. Let us say that blue segment has got another key and a resistance box attached like this. So this guy is resistance box. Either this box or any other method that can allow you to insert a very accurate specific value of resistance in the circuit, right? So whatever you have, you can have it here. And now how this method works is, let me name the keys K1 and K2. So the top key is probably K1 and the lower key here is K2, right? So initially you keep K2 open and you close K1. So how it works is, first close K1 and keep K2 open, find the balancing length, let that length be L1. So find the balancing length L1, let us say. So when you find out the balancing length and key K2 is open, no current will flow in this blue segment. No current will flow in the blue segment. If you have found the null point, then no current flows in this cell also. So even though the cell has got an internal R, because no current flows through it, the voltage drop across the ends of the cell is still equal to E, right? And you will get the equation E naught by L naught. L naught is the length of AB. Let me show that there. So L naught is the length of AB. E naught by L naught will be equal to E by L1. So the equation that you end up with is, so therefore E naught by L naught is equal to E by L1. Or you can find E from here. It implies E is found. Now what you do in the second part is, you close both the keys. Close K1 and K2 both. So when you close keys K1 and K2 both, there will be a current in the main circuit and there will be a current in this auxiliary circuit, and these two circuits will be independent of each other. This circuit is a totally different circuit and this is an entirely independent circuit. No current from the main circuit will flow into the auxiliary circuit. No current from the auxiliary circuit will flow into the main circuit. That's very easy to prove. Let us say when key K1 is closed, so I'm closing K1, and when K2 is also closed, so I'm closing K2 also. Let us say that this cell E naught gives out a current I naught. So there is a current I naught coming in, and this I naught current will reach junction A. So once this current I naught reaches junction A, it has got two options. It can go into the orange wire or it can go down into the auxiliary circuit. But if any part of this I naught goes into this auxiliary circuit, there is no way that it can return back to the cell E naught, because the jockey is in air, right? It is not joined to this orange wire anywhere. So if the jockey is not connected to the orange wire anywhere, this I naught will not break at A and I naught will completely go into this orange wire. So I naught goes into that, and this cell E sends out a current I in the circuit. So let's say there is a current, a blue current I in the circuit here, and this current I will again have the option, sorry, it's not I naught, it's I. So this current I will have the option of breaking into two parts here, but if it breaks into two parts and one part goes to A, then that part has no chance of coming back to the cell, because there is no contact at this jockey place. The jockey is still in air. So if the jockey is in air, if it is not put in contact with anything else, then the I naught current of the main circuit will remain in the main circuit, and this I current of the auxiliary circuit will remain in the auxiliary circuit. right? So this current I will just flow like this in this auxiliary circuit I. And let me take 2 points, people. Let me call this point here as B, and let me call the other end point of the cell as C. Now when I have got the jockey in air, then there is a certain drop between B and C, and the drop between B and C will be E minus IR. I know that. And so the voltage difference between B and C is E minus IR, and if I find out wherever the null point is, then the null point will be showing me a length corresponding to E minus IR, right? So that's what I do. So close K1 and K2 both, find the balancing length L2. Find the balancing length L2. So once you have found out the balancing length L2, you can say that E0 by L0 should be equal to E minus I times small r divided by L2. This is the second equation that we will get. But then we don't know the current. We don't know the current I that is flowing in the auxiliary circuit. So one way to figure out what this current I is, right, is to actually insert an ammeter here. So what some people do is they insert an ammeter here in the circuit, and they find out the value of I shown in the ammeter, and they use that current here. So because E is known from the first part, I is known from the ammeter, and L2 is known from this experiment, R can be found out. But that R will have errors. It will have error because when you have inserted ammeter here, right, this ammeter would have introduced some amount of resistance in the circuit, and we will not know how much is that resistance because we don't know how much is the exact value of R that ammeter has. We know that it is close to 0, but it is still something. So other people, what they do is they don't prefer to put this ammeter in the circuit. They remove this ammeter, and what they do instead is they use the resistance box to insert a very precise value of R inside, right, in the circuit. Now they say that in this blue segment wire BC, so there is a blue wire between B and C and a pink wire between B and C, and they say that E minus IR is the voltage drop between B and C found using the pink wire, and I can also find out the voltage drop across B and C using the blue wire, and that should be equal to I times big R, right? So what they say is that any current that the battery sends out will have to go in this small r and also in this big R here. So let me write a big R for the resistance box, and so I is equal to, since I is equal to E divided by R plus R, right, so therefore E minus IR becomes E minus E by R plus R times small r, which is E multiplied by big R divided by big R plus small r. Right, and then we can use this fact. We can use this guy here in this equation, and we will get, so therefore E0 by L0 will be E minus IR by L2, but E minus IR itself is ER divided by big R plus small r divided by L2, right? And then I will use equation number 1 and equation number 2. So let me call this equation number 1. So even if you don't want to explicitly find out the value of E, that's fine. You can just divide equation 1 and 2. So when you divide equations 1 and 2, the left hand side of equation 1 is E0 by L0, and the left hand side of equation 2 is also E0 by L0. So that term will go off. So therefore 1 divided by 2 gives you 1 is equal to, on the right hand side you will have E by L1. So you will have E by L1 divided by the right hand side of equation number 2, that's ER by R plus R into 1 by L2, and you can then solve this very easily. You can say this is E by L1 multiplied by R plus R times L2 divided by ER, and E can be cancelled out, in these expressions, and you have got the answer as L2 by L1 times R plus small r by big R. Right, and keep in mind that L1 and L2 have been found using experiment, and small r has to be found, not a big issue. And big R is the resistance box that you have inserted in this entire circuit, and that gives you a very accurate value of R that you have inserted, right? So this equation then will give you the value of small r. Right, so if I just rearrange this equation on the top, I will take L1 and L2 to the left hand side. I will get L1 by L2, and on the right hand side I will just have big R plus small r by big R. That's here. Find out the value of small r. No two B points. One is a pink B, the other is a blue B. So my bad, I should not have taken that as B. Let me take it as something called D or something.